Interstellar travel may be impossible in the most important sense, not because we lack courage, but because the laws of physics make the price explode faster than any civilization can realistically pay. I know how that sounds like someone declaring the future canceled, but stay with me, because in a few minutes we'll connect rocket engines, time dilation, black holes, and information into one story, and it changes what impossible really means. First, let's be careful. When we say interstellar travel is impossible, we don't mean no object can ever reach another star. Nature does it constantly. Dust drifts, comets wander, even planets can get flung into interstellar space. We mean something narrower and more human, fast, repeatable, civilization-scale travel like go to another star and return within a lifetime, or build a network of star systems that trade, visit, and stay culturally synchronized. And we also don't mean physics has issued a final verdict. Physics rarely offers that kind of absolute closure. What we can say based on pillars that have been tested relentlessly, like special relativity, general relativity, and quantum field theory, is this: the universe appears to enforce a set of constraints that make rapid interstellar travel either unbelievably expensive, physically hazardous, or entangled with deep paradoxes about cause and effect. Physicists like Leonard Susskind have often emphasized a theme here. The universe isn't just a big empty stage. It has bookkeeping rules about energy, information, and causality that you don't get to ignore just because you want a shortcut. And here's an open loop to hold on to. Later we'll circle back to black holes because, weirdly, the best lessons about traveling between stars come from the most extreme objects that barely let anything travel at all. We're used to cost that scale gently. Drive twice as far, buy roughly twice as much gas, build a bigger ship, carry more supplies. Interstellar travel doesn't behave like that. A better analogy is a hidden cost curve. Imagine a video game where the interface lets you upgrade your speed 10%, 20% faster. It feels linear. But behind the UI, there's a secret rule. Every upgrade multiplies the price. On paper, 90% of light speed and 99.9% of light speed look close. Just a few digits. In reality, they are separated by an enormous wall of required energy. This is one of the oldest traps in physics, confusing the map for the territory. Our minds are classical. We expect that if we push harder, we go faster in a fairly straightforward way. Relativity says that intuition is an approximation, useful at everyday speeds but not fundamental. And here's the key reframing. Near-light travel isn't primarily about moving through space. It's about changing your relationship to time. You are trying to force the universe into a regime where time, for you, flows differently than it does for everything you left behind. That's not free. In a moment, we'll talk about energy. But keep this in mind. In relativity, energy is not just fuel. Energy is also gravity, and that single fact brings black holes into what seems like a simple travel problem. Let's start with something unromantic: propulsion. To accelerate, you need to change momentum. To change momentum, you have to exchange momentum with something else. That's not an engineering tradition. That's conservation of momentum. In practice, rockets throw mass backward. If you don't want to throw mass, you can throw light photons, but then you're paying a steep price because light carries relatively little momentum per unit energy. And so even before we talk about exotic drives, the basic problem is that pushing a macroscopic ship to relativistic speed demands extreme energy. And there's a second layer. When you carry your fuel itself has mass, and you have to accelerate the fuel too. That creates a compounding problem. The faster and farther you want to go, the more fuel you need. But the more fuel you need, the heavier you become. So you need even more fuel. You don't need equations to feel the cruelty of that loop. It's like trying to carry enough food for a journey, but every extra pound of food makes you burn more calories, which forces you to carry even more food. There are clever ideas to reduce this: beam sails pushed by lasers from home, fuel scooped from space, stage ships that drop mass, or propulsion methods with higher efficiency like fusion or antimatter. Some of those are physically plausible in principle, but plausible in principle can still be functionally unreachable in practice, especially when you add the next wall. Because as you push toward light speed, the universe starts charging you in a very particular way. You spend more and more energy for less and less gain in speed. At low speeds, extra energy mostly becomes extra speed. At high speeds, extra energy mostly becomes you are harder and harder to accelerate. And that's just the price to get moving. The price to survive the trip is another story. Space is not empty. Between the stars, there is thin gas, mostly hydrogen. There is dust. There are cosmic rays. And bathing everything, there is background radiation left over from the early universe. At everyday speeds, this is barely noticeable. At relativistic speeds, it becomes a nightmare. From the ship's perspective, everything in front of you gets compressed and energized. Radiation in the direction you're moving becomes blue-shifted. It increases in energy. Sparse particles become frequent impacts, and those impacts become violent. A dust grain that would gently tap your spacecraft at slow speed can behave like an explosive projectile at high speed, not because the dust changed, but because you changed the frame. So now you need shielding, but shielding adds mass. Added mass raises the energy you need. Higher energy often implies higher speeds, which makes the radiation problem worse, which demands more shielding. The problem loops back on itself again. And there's another twist. The shielding doesn't just need to be thick. It needs to handle secondary radiation particles created when high-energy impacts generate showers of other particles. In extreme regimes, your shield becomes a particle physics experiment. So even if propulsion were solved, the trip itself turns the interstellar medium into something like a hostile environment that scales badly with speed. And you might think, fine, so we won't go near light speed, we'll just warp space. That's where the deeper walls appear, walls built out of causality and information. Here's the temptation. Instead of moving through space faster than light, reshape space so the journey is shorter. A wormhole, a tunnel, a warp drive, a bubble of spacetime. General relativity allows spacetime to curve, and that can make shortcuts seem imaginable. But the moment you talk about faster than light travel, whether by a ship, a signal, a wormhole mouth, or a warp bubble, you collide with something more rigid than speed. You collide with causality. Causality is the rule that causes precede effects. It's not just philosophy. It's built into how relativity stitches together space and time. If information can travel faster than light, then different observers moving relative to one another can disagree about the order of events. In some perspectives, the message arrives before it is sent. And once that door opens, you can often build loops, send a message that prevents itself from being sent. You don't just get faster travel, you get contradictions. Now, is it logically impossible that nature permits some consistent faster than light mechanism? Not, but what we see across many theoretical explorations is this. Whenever a setup looks like it enables causality violations, the physics tends to fight back. Sometimes it fights back by demanding exotic forms of matter or energy that we have never observed in the required forms. Sometimes it fights back by making the configuration unstable. Sometimes it fights back through quantum constraints that limit how much negative energy you can accumulate and for how long. Important clarity negative energy effects do exist in quantum field theory in small, subtle ways, but turning them into a macroscopic engine is another matter. The known constraints are severe. So if your interstellar dream depends on just make a stable wormhole or just build a warp bubble, you're not merely dealing with engineering, you're negotiating with the universe's consistency rules. And that brings us to the strangest teacher in all of physics, black holes. Because black holes are where causality, horizons, and information collide. A black hole is often pictured as a cosmic vacuum cleaner. That image is misleading. A better operational definition is this. A black hole is a region of spacetime surrounded by a horizon, a one-way boundary. Cross it, and you can no longer send signals back out. That's already a travel story. A black hole is the ultimate no-return trip, not because of some material wall, but because of the geometry of cause and effect. Now, here's the shock that changed physics. Physicists like Jacob Bekenstein and Stephen Hawking discovered that black holes behave like thermodynamic objects. They have temperature and entropy. Entropy is roughly missing information the number of microscopic ways a system can be arranged while looking the same macroscopically. And the black hole's entropy scales with the area of the horizon, not the volume inside. That's profoundly non-classical. Our everyday intuition says more volume means more room for stuff, more room for information. Black holes say no. The maximum information content of a region is bounded by its boundary. This is one of the roots of the holographic principle, the idea that at a fundamental level, physics inside a volume might be encoded on a lower dimensional surface. Now, why does that matter for interstellar travel? Because every shortcut proposal that tries to manipulate space-time aggressively is also, in some sense, trying to manipulate horizons, causal structure, and the flow of information. Black holes suggest there are deep constraints on how information can be stored, transmitted, and recovered when space-time becomes extreme. And then there's the famous black hole information puzzle. If something falls into a black hole, does the information disappear forever? Hawking's early calculations suggested it might, but that would break a foundational expectation in quantum theory that information is preserved. The modern consensus among many physicists is that information is preserved, but the mechanism is subtle. It seems to be encoded in correlations and in the structure of the horizon itself, again pointing toward the idea that boundaries matter more than we classically expect. So when someone proposes a wormhole you can casually walk through like a subway tunnel, a physicist's brain immediately asks, what happens to information? What happens to causality? What happens to the bookkeeping? And here's the next open loop. There is a place in modern theory where these ideas become unusually concrete, a proof of concept that space-time geometry can emerge from quantum information. It's not a blueprint for building quartals, but it's the closest thing we have to a controlled laboratory for these questions. In the last few decades, theoretical physics developed a remarkable idea often associated with Juan Maldacena, ad CFDF. In simple terms, it's a duality, a dictionary between two descriptions that look totally different. One description includes gravity in a certain kind of space-time called anti-de Sitter space. The other is a quantum field theory without gravity living on the boundary of that space. The breathtaking implication is that a gravitational world in a bulk volume can be equivalent to a non-gravitational quantum system on a lower dimensional boundary. That's holography made real, at least in that special setting. Now, we have to be humble here. Our universe does not appear to be exactly anti-de Sitter space, so this is not a direct model of our cosmos. It's a controlled example that suggests the holographic principle is more than poetry. And once you accept that geometry can be encoded in quantum information, you start seeing why the universe might be so strict about causality and information flow. If space-time itself is tied to information theoretic structure, then breaking causality may not be like breaking a speed limit. It may be like trying to write a contradiction into the operating system. This is also where wormholes re-enter the conversation in a more nuanced way. There are deep connections still actively researched between entanglement and wormhole-like geometry. You may have heard a slogan that entanglement and wormholes are related in some way, but slogans are not engineering. In certain theoretical models, wormhole-like structures appear as geometric representations of quantum relationships. Under very special conditions, there are even results where something can be made traversable in a limited sense, typically by carefully arranged quantum effects that involve negative energy like behavior. But these are not the cinematic wormholes of science fiction. They are delicate, constrained constructions in idealized models. And importantly, they tend to preserve causal consistency. When a configuration threatens paradoxical signaling, the setup usually pays a price, instability, back reaction, or constraints that prevent the would-be time machine from functioning as advertised. So AdCFT doesn't say, wormholes are real and we can build them. It says something more subtle. Space-time, information, and causality are entangled at a deep level, and naive shortcuts usually collide with that fact. Which brings us to emergence. Because if space and time are not fundamental, then distance may not be the kind of thing you can simply bulldoze through with enough horsepower. Emergence is one of the most misunderstood words in science. Emergent doesn't mean fake. It means derived. A single molecule doesn't have a temperature, but a huge collection of molecules does, and temperature becomes a powerful, real concept. Likewise, the solidity of a table is emergent. At a deeper level, atoms are mostly empty space and quantum fields, but the table is still real. You can't walk through it. The emergent description matters. So if space-time is emergent, if it arises from deeper quantum degrees of freedom, then it can still be real in every practical sense while not being fundamental, and that matters for travel. Because the dream of interstellar travel often assumes space is a passive container, but in an emergent picture, the container is part of the system. There may be fundamental limits on how it can be reconfigured without breaking the rules that keep physics coherent. Here's a thought experiment. Imagine you have infinite engineering skill, perfect materials, perfect computation. You can build anything that doesn't violate fundamental laws. Now ask, what exactly are you trying to do when you try to outrun light? You're trying to move information, the fact of your existence, your choices, your state, from here to there, faster than the causal structure allows. If space-time and causality are emergent from deeper rules, then outrunning causality might be like trying to make a higher level phenomenon violate the constraints of the lower level system that generates it. You can't build a boat that sails upstream faster than the river's own flow. If the river is what defines upstream and downstream in the first place, that's not a proof. It's an intuition. But it matches the pattern we see. The closer you push toward the boundaries of causality, the more the universe demands extreme energy, extreme conditions, or exotic ingredients, and then punishes you with instability or paradox. Now let's close the loop on what impossible means with three concrete implications. Established physics allows a spaceship to approach light speed arbitrarily closely in principle, but in principle hides the scale of the cost. The energy required becomes enormous, not a lot. Enormous in the sense that it competes with planetary or stellar energy scales for macroscopic ships. You can try to reduce ship mass. You can imagine tiny probes pushed by giant lasers. You can imagine sending gram-scale sails to nearby stars, and some projects seriously study that. But the moment you scale up to human payloads, shielding, life support, redundancy, and safe deceleration at the destination, the energy and mass budgets balloon. So the first implication is not no one can ever go. It's that the kind of interstellar travel we instinctively imagine routine, fast, and scalable may sit on the wrong side of a compounding curve. Time dilation is real. It's measured. GPA satellites correct for relativistic effects. If you travel close to light speed, you can cross great distances while experiencing less time on board. So, yes, relativity offers a kind of personal loophole. From the traveler's perspective, the galaxy can become smaller in time. But from the perspective of everyone else, the trip still takes years, decades, or more. That means interstellar travel can become a one-way cultural separation. You don't visit another star system and come back to tell stories at the same dinner table. You return to a different era. So even if near light travel is possible, it doesn't automatically create a connected interstellar civilization. It creates explorers who effectively step into the future. The most dramatic versions of interstellar travel wormholes and warp drives are not just harder, they are different in kind. They attempt to beat the causal structure itself. And this is where the best we can honestly say is general relativity allows exotic space-time geometries mathematically. Quantum field theory allows small negative energy effects, but strongly constrains them. Many apparent faster than light schemes demand negative energy densities in amounts and configurations that may be unphysical. When a setup seems to enable time travel like paradoxes, it often becomes unstable or inconsistent once you include the full physics. This is an area where some details are speculative, and researchers disagree about what the final rulebook looks like. But across approaches, the trend is striking. The universe behaves as if causality is not optional. So impossible here may not mean forbidden by a single line in a textbook. It may mean blocked by a convergence of deep principles. So what's the physics that makes interstellar travel impossible? Not one law, a stack of them. The speed of light acts like a structural limit on cause and effect. The energy required to approach that limit grows brutally. That energy brings radiation hazards and, in extreme forms, gravitational consequences. And the flashy shortcuts collide with the universe's bookkeeping causality and information. Black holes taught us that information and geometry are linked in surprising ways, like entropy scaling with area. Holography hints that spacetime may be an emergent description with deep constraints we're only beginning to understand. Now, the most important nuance, emergent doesn't mean meaningless. Even if interstellar travel in the science fiction sense is out of reach, that doesn't shrink our world, It expands it because our solar system alone contains oceans under ice, ancient worlds, and resources beyond anything we've ever managed. The next centuries could still be a golden age of exploration, just not the kind where we casually hop between stars. The stars aren't forbidden, but the universe does not offer them at a discount. If you want more slow, intuition first science documentaries like this, subscribe. And here's the question to leave in the comments if you had to bet. What's the true showstopper for interstellar travel energy? Radiation, causality, or something we haven't discovered yet?